So the plan for today is to talk about 808 and PC hardware and x86. So one way to think about this lecture is sort of a brief overview of 004 in a single lecture, but then not focused on the x86 exposed to the data. If you know everything about x86 programming already, this is it's going to be a pretty boring lecture, but it's useful for everybody else to actually do lab 1. Most of you who has looked at lab 1, you're going to go in a minute. Okay, good. So you'll see a lot of this familiar. Hopefully, will help you along getting going. All right, we just want to make sure that everybody has the same starting point. So while you're working in QMU and on your lab 1, you might forget what a PC looks like. And this is a PC, and you're writing software for a PC. And so we don't really care the outside, but we want to look at the inside. And we actually want to go over the following topics. We're going to talk a little bit about what is in a PC. Then I'm going to talk a little bit about the x86 instruction set, which you have to be familiar with. You will get more and more familiar with it as you proceed through 808. We really don't dedicate complete topics to it, but as you go through it, you'll pick it up. You look at some code and say, hey, what does this instruction do? And most of them you can guess, but a couple of them you probably have to look in the reference manual. We'll go over the GC calling conventions as we use them in 808, and then we'll talk a little bit about actual black box or QMU does on the inside, so that you have a little bit of idea, like what are the tools that you're using, okay? So there's a lot of this is sort of a tool lecture for 808. Okay, so this is the inside of a PC, or at least an older PC. I brought one here just to make sure that you see one. Because you won't see it the rest of the semester, but basically this is what you program, correct? So you'll be poking at this continuously and writing instructions to poke particular components. And so it's interesting to see what it is. So a couple points. So when people talk about the motherboard, there's this digital board in the back, and you see there's it's called a motherboard because there are all the daughter boards, which are these little things that stick into the motherboard. This is actually the x86 processor, except you can't really see it because there are all kinds of heat. There's a heat sink on it, a big heat sink, right? So it is there. These are whatever. These are a hard drive, right, that you will be programming when you write an IDE driver. This is the thing that actually is going to do something for you, hopefully. I'm going to pass this around, but here on the side under the CD-ROM, there's actually the memory, a little daughter board with a lot of memory chips on it. And then all these cables, they're basically buses, different types of buses. As you will see, and also in this lecture, we'll see that PCs and x86 processors have evolved from one design to a completely different design, but it's always backwards compatible. So basically every bus, every wire, every different type of bus has a different type of set of wires, and they're all in here. So, this is the so this is an IDA drive, so this is an IDA bus, and this was the PCA bus. It's much more digital than these little cables that are floating around. Okay. There's a battery. Here's the battery. If you care. This is we won't see that much, but this is sort of interesting to see. This is the North bridge, and this connects basically the processor to the memory and to the faster buses. This is called the South bridge. This chip here, which actually connects to the slower buses. Right? So you want to be programming that, but you'll see sometimes the term North bridge and South bridge thrown around. They're basically just connectors, if you will. All right. So I'll pass it around. This is an old PC from 2003, so modern thing doesn't look like this anymore, but this is easy to carry around. So there's one of you pass it around. So, all right. So although you'll see. We'll go through and actually you see one of the drivers actually will be poking at all these different devices at different pieces of the code. We're going to mostly abstract everything away, and we're going to think about PC, and most of the source code will be thinking about it in this term. There's a central processing unit, CPU, like the thing that was under the sink, heat sink. There's some memory, and there's I/O. And sort of from our point of view, we can take a very abstract point of view. We don't care about the wires, we don't really care how the devices look like. This is the picture that we're getting mostly looking for. And the CPU, is in charge of sort of those instruction processing, Memory stores, long values. The blue there is content when you power off the machine, and then input and output the devices and everything else. Whether it's a CD-ROM, an IDE drive, UPGA display, whatever. And we're going to be, in each of them is a slightly different interface. But we're going to not care about that too much for this lecture. So one of the, as I said, this is mostly a 004 review. One of the things that this PC or x86 falls into is a stored program computer. Early on, computers were sort of hardwired to do a single thing. This is very, very early on. And then there was a real invention to say, like, well, we'll separate what, we're going to describe separately what the computer is supposed to compute from what actually the processor does. So in fact, what the computer is supposed to be doing is a set of instructions that are stored in memory, these memory chips that you remember we've seen, plus some data, as the rest of the memory, for the rest of the memory where the content is stored. And the CPU does nothing else basically than interpreting instructions. It just goes through one instruction at a time, interpreting, perform whatever the what the instruction is supposed to be doing on and modifying, perhaps data. Right? And so, this is sort of one level of indirection, which makes the computer much more general purpose, because now you can run any type of computation sort of on the computer, right? By describing through a set of instructions. The x86 implementation is exactly like that. There's one register called the IP, or the instruction pointer, in the 32-bit mode. It's an EIP, and basically it points to the next instruction to be interpreted. And so the processor, will look at the address that's stored in the EIP, look at the memory location, see some bits in that memory location, interpret that as an instruction, and then execute whatever that instruction is supposed to be doing. All right? And then it increases the instruction pointer. Now on the x86 that's slightly complicated because instructions are variable length. So unlike the Beta where everything's nice and well designed, the x86 is a mess. Some instructions are a single byte. And other instructions, I think instructions are 13 bytes. I can't remember what the longest one is.
It's 16 or something.
16? Yeah, whatever. So the longest one is 16 bytes. And so increasing the instruction pointer actually is complex.
No, you can't make longer instructions, but it'll throw an exception.
Okay, it'll throw an exception. Okay, so after the instruction is executed, the EIP is now increased by the appropriate value, whatever the length of the instruction was. Okay? The EIP itself, the register, does get modified. In fact, instructions can modify it. And so the instruction can modify call instructions, which we call a procedure call, and we'll talk a lot more about this in a second. Return, which returns from a procedure call. Jump, which goes to a different location, where it basically says, like, jump to this other location in memory and interpret instructions there. And conditional jumps, which allow you to implement if statements and things like that. Right? Now, a computer doesn't do much if you can just have an instruction pointer. So, there's a bunch of registers. You can think about this in sort of temporary stretch, places where you can write little values, as the processor is computing. And here are the registers on the x86. You can see there, first of all, x86 evolved from the 886 to the 286, 386, 486, Pentium, and a whole generation of processor. As I said before, they're all backwards compatible. And you will see that in all the notations. So it started out basically as an 8-bit machine, correct? And so you have the registers A, the register brilliantly named A, B, C, D, E, etc. And A, you can see there's a lower half and a higher half. The H is high, L stands for low, and the two, their 8-bit values together they form a 16-bit value. When at some point, Intel decided, well, 16 bits is not enough, 32 bits, they put like you have the AX value, and then you have the EAX, and that means it's a 32-bit value. All right? And so you've got to be a little bit core. For example, in the bootstrapping code, where the bootloader goes from basically pretending to be an x86 and going through to sort of being a modern x86, you will see that the instructions are very carefully either using AX or EAX, etc. Most of the assembly you'll be looking at is all going to be 32 bits, so you don't really have to worry about it, but it's important to know that it's there. Now, there's a bunch of registers that have, by convention, used for particular purposes. They're not required to be used in that way, but they typically are. And so, for example, BP, which we talked about, base pointer register, and then SIDI, which you mostly don't see, and then SP, which is a step pointer, which you will see a ton of. We'll be playing around with. Okay, and then so these registers are used by instructions, to compute values quickly. You can access the register sitting on chip itself, not separately, not on the bus, north or south or west or east of the north bridge or the south bridge. There's something actually on the chip itself, and it can be accessed in a single cycle, basically. Okay? And so instructions that work on this are like subtract, sub, add, which is addition, and, which is logical and, etc., etc. The usual instructions that you must have seen, most of them in .04 or in some other form of computer organization. Okay? The way the x86 does conditional jumps and things like that is based on bits that are in the E-flex register. So the E-flex register has a whole set of flags, ranging from say overflow, trap, sign. So the one, for example, that you might see a lot is the sign flag, or the parity or carry flag. Actually, the one you see most is probably internet enable flag, which is a very OS specific flag. But basically, instructions as they go through, some of the instructions as a side effect of executing the instruction will set a value, set a bit in the flex register. So, for example, if you test instruction, test EAX, well, you compare it to a 0, and then that will set, the 0 flag, yes or no, depending on whether actually EAX contains a 0. Okay? So that doesn't do any jumps, it just, sets that bit into the E-flex register. But then, of course, you can jump based on values in the E-flex register. So if you say jump not, GNZ means if it's not 0, jump. And so not 0 is then whatever, the 0 flag actually implies. Okay? So a jump typically takes two instructions. One, sort of to compute something and set a flag in the E-flex register, and then the actual jump instruction that jumps based on the content of the E-flex register, or a bit in the E-flex register. Make sense? So we saw there's not that many registers on the x86, so we're going to use more memory, more workspace. And these are the typical instructions you will be seeing. They should be reasonably familiar. You can there's move along from the register to the register, and that's the register mode, the memory instruction. There's move along from dollar something to EDX. That's immediate, or immediate is a constant. So $0x123 really means we're going to take the value 0123 hex and move it into the register EDX. As opposed to the next instruction, where OX123 is actually interpreted as an address. And so we're going to move the value stored at that address into EDX. That's what the third instruction means. Right? The equivalent is written down in C on the middle column. Right? And you use this sort of casting. So how many people are really familiar with pointers? Lab 1 will make sure that you're familiar. Okay, great. So it should be all easier to read this, correct? And so for your C programmer, maybe the middle finger is an easy way of remembering actually what these instructions do. The fourth form is typical indirect. Basically we're going to use the value that is in the register as the address from which we're going to load the value. Okay? And then the last one combines the indirect plus a displacement. You take the value that's in the register, add 4 to it, and then you take that as the address from which you're going to load the value. Okay? Now in x86, move, you have specific memory instructions like move, push, and pop, which we'll talk about in a second. But most instructions actually can take actually a memory instruction. Okay, so unlike the data, right, where only a few instructions can actually take, only memory instructions can take a memory location address. And most instructions only work on registers. In the x86, for example, a sub, might actually take a memory address. Okay. So the x86 has specific instructions for the stack. We'll talk a little bit about stacking in a minute. But the mechanics are pretty straightforward. You can push a value onto the stack. So push along moves whatever the count of EAX is, and move pushes on the stack. Pop does the opposite. And call, okay, so these are, that's actually not really a stack operation, but call basically takes an address. It takes an address, pushes the current AERP actually on the stack, so that later on you can return to it, and then actually changes the counted at the EIP to be equal to 1, 2, 3, 4, 5 in hex. All right.
Which is the next EIP?
Which is the next EIP, sorry. Yes. So not the, after the values increased. And in return, does the, pops the top of the stack and uses that and pushes that into, pops that into the EIP register and then jumps to that particular value, or interprets the next instruction from that location. Okay? And this is implemented procedure calls. Right? And we'll talk a little bit more about it in a second. And you really have to understand this, because you will see that you have to understand stacks pretty carefully as we go through. So a little bit more about memory, because in the x86 it's complicated. Everything is complicated in the x86, and there's any way of doing anything. Again, this is all mostly because of backwards compatibility. So you'll see a bunch of other registers, namely like CS, code segment, SS, stack 7, DS, data segment, and then a bunch of others that you won't see much about, and you can ignore generally. They are what are called segment registers. Segment registers actually have different types of semantics depending on whether you're running on an 886 or an 386 or later. Originally, they were nothing else than basically offset. So the problem in the 886 was that the registers were 16-bit, but memory addresses, the bus addresses, were 20 bits. So you miss 4 bits. Right? And if you don't use those 4 bits, you can't reference higher parts of the memory. And so the way an address is actually constructed on the 886 is you take a segment selector, or you segment register, the value stored in it, and that's actually your top 4 bits. And then whatever is in the register, for example, in your IP or in your stack pointer, is the remaining 60 bits, and you combine them together. They call it, sometimes called in the x86 literature, they're called logical addresses because they combine segment and regular registers in address. Okay. This turns out to make life incredibly complicated because now you suddenly have sort of 2 types of addresses: nearby addresses and far away addresses. Value stored in the stack, you don't know exactly what it is, and so for most of the things that we're going to be doing, you can ignore it. And in fact, we'll basically we set things up and generally to ignore segments as much as we can. But where you will see it is actually in the bootloader and when this machine actually gets off the ground. All right, so at least you know what these are. You're going to see them again because at some point, the 386 and 32-bit addresses compete with the, at that point, very popular Motorola processor, which was a complete 32-bit processor. And now the second selectors didn't really work because all the memory protection and all the kind of stuff that we'll be talking about next week. And so the second registers are not a value that is just appended, or it's not the top. Don't take the top 4 bits and put it, or you append it to the address or prepend it to the address. But instead, what you do, you use it as an index into a table, and that table will tell you what the starting point of that segment is. You'll have to program the table in a few places, but again, we're going to try to set up everything so we can ignore segments. Okay? So basically, I'm talking a lot about things you're going to be hopefully ignoring, but you need to know once in a while that will show up and you're going to be surprised. For most of this lecture, I'm sort of going to assume that whatever addresses the x86 generates are the same as actually what the memory interprets or uses. Next week, or actually on Wednesday, we'll change that, and you'll see that actually the x86 executes virtual addresses that are going to be translated through page table hardware or to actually physical addresses. And so there's a bunch of other support that I'm just going to skip because we're going to talk about it on Wednesday. So I talked about the processor. I talked about memory, which was the two of the 3 abstractions. I showed earlier on the 3rd abstraction is I/O. All the stuff you need to do to actually get a device to do something. So here is a minimal, if you will, device driver for poking at the line printer port. And so what it actually does, it prints out a single character, where NC is the character to be printed. And look at this instruction. The first thing it does, it actually looks if the line printer is currently busy. And the way you do that on all 86s is you use the INB instruction. There's a separate, if you will, there's the memory space, ranging from 0 to 2 to 32, -1, and then there's a separate I/O space. And the I/O space, that's where all devices live. You'll see later new devices live somewhere else, but in the old, in the early PCs or the x86s, the devices lived in a particular range, which used the instructions INB and OUTBUI for. And you can see, that by agreement, PC manufacturers agreed on this, that the line printer, the status port sits at address 379 in the I/O space. And so every PC agrees, that is actually the location for the I/O, for the line printer status port, right? And so you have to find those in manuals. They document it, they say like this or this and that register, and then you can write the code that actually does the right thing. It doesn't matter if your PC is produced by Dell or HP or somebody else, they all agree on this. So the first thing it does, is INB actually reads basically a byte. The B stands for byte. From, you will see further earlier on we saw L, that stands for long, which is 32 bits. Because every instruction can come in a 32-bit version, a 16-bit version, or an 8-byte version, you have to actually indicate in the instruction opcode which one you want. Okay. So INB reads the value of the, basically does, ask the line printer to return the status of the printer by reading that status port. It checks if the busy flag is set, which is, turns out to be 80, OX80, right? So it's the, not the first 4 bits, but the next 4 bits, you're going to check if actually the busy flag is set. And this again is agreement, right? So you got to find this in the manual or whatever, and build the line printer, so it said like, okay, this is how the line printer works, and if you want to program the line printer, this is what you're supposed to be doing. Right? And so, it goes through, checks if busy. If it's busy, it spins around. Just waiting till something happens. This is called a spinning loop. We'll see that's actually pretty inefficient, and later on we're going to get much more sophisticated about it in terms of how we interact with devices. Because now the process is doing nothing, right? Like just waiting on the device. It'd be nice, basically, if the device could go off and do something while the processor does something else. And so we're going to use interrupts to orchestrate that. But this is a very simple driver where you can do this. And once it's not busy, we actually publish. When we we do an OUTB instruction to tell the line printer, please, print the character C, and puts it in the data port so that the printer knows what to do, and then we tell the printer to actually do it. And so this is a typical way, when you write a device driver. You wait for something, you put the right values in the right places, and then you tell the device to do something, and then you wait until the device is done doing it. Now this is a very simple device, so it fits in 8 lines or 10 lines of code. But complicated devices, it will be much, have a lot of different features, and so programming them is much more difficult, and so the device driver gets a lot more complicated. And you will see that when, for example, the network driver you're doing is quite a bit more complicated than this one with the ID driver. Okay, but this is a driver in a piece of code. Now it turns out, of course, in the wisdom, of the early PC designers, they thought that 1024 I/O addresses was going to be enough. No reason to have more devices than that, ever. Turned out to be wrong because they were hugely successful, correct? And so they need a lot more. More devices came around, ran out of numbers, for devices, and so there's a different way of doing I/O. OUTBUI is an explicit instruction within the I/O space. More modern versions of the x86 all use memory mapped I/O, where basically particular ranges in the memory space behave differently than regular memory. Instead of, if you read or write a value to that memory location, instead of storing it in RAM, it actually happens to be the case that it actually is communicated to the device that's actually living in that part of the memory space. And the nice thing about that is that you don't need special instructions anymore, right? You don't use INBs or OUTBs. You can just use move long and those instructions to poke the device. The system control, the device controls just show up as a memory address somewhere in the memory space. And again, it has to be agreed on where they live, but you have a lot more space in a 32-bit space than an 8-bit space, right? the one thing you have to be careful a little bit about is that a read on a device actually is likely to have side effects. Right? Like if you read from memory, there's nothing that changes in memory. You get the value back, but it's often the case that when you read from a device, that will probably have some side effect. Right? So not all all read instruction is going to be side effect free. Okay. Okay. So then this is a picture you probably see a lot. On Wednesday. This is basically, the physically memory layout of the PC today. Basically, as memories got bigger and bigger, things got moved around and evolved. Right? It started out the PCs never had more than 640K. So this is called low memory because that was always available. Above it was then the VGA display, and then there was a bunch of the I/O space, what I just talked about, the old devices, and then there was the BIOS, and that was it. And so that fitted in 1 megabyte, and every PC was going to be bigger than 1 megabyte. Now, again, because it was successful, people, and my memory got cheaper. People want to write bigger computations on PCs. They're like, oh shoot, we got to have more space, and so so they went to bigger addresses, correct, and we got extended memory, which is all the memory basically above a megabyte to 4 gigabyte. Now we're going to mostly deal with 32-bit PCs. We're ignoring 64-bit, but this is just the next step in the evolution. Making addresses slightly more bigger. The newer devices, which you see actually in JAWS, I think, maybe the network driver, but the very few, the newer devices all live up in the 32-bit address space, and so they're mapped right there. So if you're typically PC, if you use a very big address, that probably means that actually you're poking or reading from some I/O device. Right. Any questions so far? And you'll see in Lab 1 where you're actually, this picture comes straight out of Lab 1, and I'm sure at the end of this class, at the end of this semester, you'll know this picture by heart. Okay, so to summarize, and use the x86 part, this is like the instruction manual except we posted the instruction manuals for the x86, and you will find out that like 3 volumes. There's a lot of instructions. Most of them actually you never deal with, and so these are the most that you're going to be seeing. And so they mostly fit on the single slide. There's the data movement instructions, arithmetic instructions, I/O instructions, control instructions, some string instructions, and then we'll see a lot of system instructions, but we'll introduce them as we go through the semester. And those have to do with traps, interrupts, all that kind of stuff, that your operating system actually needs to use to actually get the hardware to do the right thing. All right. There's a slight point of confusion, or a big point of confusion, depending on whether you're aware of it or not. There's 2 ways, there are 2 syntaxes for the instructions. The Intel manuals use something that we call the Intel syntax, which is not surprising. And what they basically have, the order is opcode, then the destination, and then the source. Right? So the move instruction, the destination is first and the source is last. We're using GCC tools, and all those tools actually use the AT&T notation, as it's called. And it actually is exactly the other way around. So it's first opcode, and then source, and then destination. So you basically read it from left to right. Neither one's better than the other. But you're going to be slightly confused maybe once in a while because you're going to look at the instruction Intel manual to see what the instruction does. But to actually use it, you may have to change the order of the operands. All right? Never really creates any problems. At some point you just goes automatically. But the first time, if you start thinking carefully about it, it's like, well, that's weird. That shouldn't work. And you just have to remember that the order of the operands are different. Okay. So this is talk a little bit about Poly conventions. Again, this is sort of one of another sort of the big ideas in computer science. Where you see already sort of stored program computers is a big idea. The memory mapped I/O is a sort of pretty cool big idea, and procedure calls and implementing procedure calls efficiently is another sort of really early big computer science idea. Right? Because it allows us to implement procedures, allows us to have abstraction, like everything that sort of modularity is built on, right? And software. And so the calling conventions, are not dictated by the x86. In fact, you can implement different types of calling conventions, and they're dictated in GCC. Basically, the compiler we're using, chooses the calling conventions. And as an OS writer, we have to make sure that we're aware of that, because in some cases we're going to fake it, that somebody did a return from a function, and so we've got to fake it reliably, precise enough that that we're writing code that couldn't be generated by the compiler, but we generate it by hand, because we need to sort of pretend it to be that we're actually invoked a function. Okay, and so it's important to know what these calling conventions are, and a good chunk of Lab 1 is about the calling conventions. And the calling conventions so it turns out, GCC has a different calling convention depending on how you configure the compiler. We're going to use a particular calling convention that is easy for us and for you, but doesn't produce the most highly optimized code. And so the calling convention is as follows. When a function f calls g, the first thing f does is actually pushes its arguments on the stack. And it does it in reverse order. And we'll talk about it in a second. So we first push argument 2, then let's say if g had 2 arguments, we first push argument 2, then argument 1. And then, you're called the x86 call instruction, right? And remember the x86 call instruction, when it did, it will pushes the next EIP onto the stack. And that is convenient, right? Because what we're going to be using that is the return from the function, so we know where we actually came from when this function g was called. Right? Which g might be called by f, it might be called by h. When g returns, we need to know whether we're going to go to f or back to h. Right? And so the EIP will tell us where actually we came from. Then we're going to save the EBP. This is the base pointer, and we'll talk about that in a second. And then we're going to point the EBP to that location where we actually stored or saved the last EBP. This is going to be important for Lab 1, as you may have noticed. Then the compiler might do all kinds of things. It might create space for local variables in the stack, and that might push the stack pointer further down. Okay? And so when we're talking about the stack frame, everything above the saved EBP is the caller stack frame, and anything below is basically the callee's stack frame. Okay? And so to allow recursive functions, the reason why stacks are called correct is because you can have recursive functions. You can just keep calling, and you get all the whole, the depth of the number of stack frames is going to be equal to the depth of the recursion. All right. So when after sort of doing this saving EBP, then the compiler generally that saving EBP is typically called the prologue. And so in a lot of code that we'll be seeing, you will see sequence of bits like push long EBP, push the current EBP onto the stack, and move ESP into EBP. Right? That does that particular first 2 operations, and they're part of the prologue. And there's a similar when the function returns, it's going to restore the EIP and the EBP. And the way it restores them is basically pushing them off, popping them off the stack. Right? So in the epilogue of the function, as long as this sequence is like this, it moves the EBP into the stack pointer, basically resetting the stack pointer to the base pointer, wherever the saved base pointer was, and then it restores the base pointer, and then popping the EBP, which is going to be then the returning address. We'll see that in a second. In fact, in your handout and your code that you already have, you'll see that this code is there. There's a couple more components of the procedure call conventions, which are important. The rules are as follows. In GCC, when the code is compiled, generated in GCC will put the return value of a function in the register EAX. And so you'll see often in the assembly code that we're actually looking at EAX because that's where the return value is actually of the function is stored. And then there's a couple other rules that the callee may do anything it likes with ECX and EDX. If the caller cares about them, it's the caller's job to save them first before calling G. So if F cares about the value of ECX and EDX, and wants to make sure that they stay, it has them after the G returns. It's its job, F's job, to actually save them first. Okay. And the other part of the contract, procedure called contract, is that the callee is not allowed to change EBP, EBX, ESI, and EDI at will. If it wants to change them, it first has to save them. Then it can change them. Before returning, it has to restore the old values. We already saw that with EBP, that it saves it on the stack and restores it at the epilogue. Okay? This is again important because you're going to, when you're doing interrupt processing, you're going to got to make sure that, and you need some registers to actually in your assembly to actually get everything set up right. Certain registers you should not use because you're not supposed to trash them, or if you do trash them, you first have to save them and restore them then later. And this can be the most obnoxious bugs, right? Like you forget to save one register. Most of the time the code's going to work perfect. Whatever, it doesn't turn out to be anything important in that register. Once in a while, it turned out to be something really important in that register, and your system just stops working. Right? And so you got to be, you got to understand when the rules apply and what you need to do. Luckily, we'll be writing very little assembly, and so you don't really have to be too much aware. But whenever you have to write assembly, you got to be very, very, very careful. Remember, it's not like C compiler takes all the care of this for you, but when you're writing assembly, you got to follow the same conventions. And so, writing assembly, even as a few instructions, can be a lot more complicated because you got to go through your head and make sure that you didn't really do anything stupid that is going to cause some major pain later on. Okay, so these are, and the typical language that's being used for this is the register solid saved by the caller, called caller saved, and the register saved by the callee are called callee saved. Good. Okay, so here's a little example, just to get this all. So we have a brilliant C program on the left, and a function main, it calls the function f with one argument, passing a to it, and it adds 1 to the result. What does f do? F calls g, right, passing x, and then g actually adds 3, to that argument. Okay, and on the right, we see actually the assembly code generated, by GCC, without any optimizations. You might wonder, like, wow, that's a lot of instructions to compute, 8 plus 1 plus 3, right? Could be a lot. Compiler clever, just print out the answer. But this is what's generated without any sort of optimization. And you see that every function has sort of a prologue, a body, and an epilogue. And so the prologue is like the stuff that needs to be done before the function runs, correct? And we've done it before. You see that on the top, like in main, pushes the EBP, and then sets the EBP to the current value of the stack pointer. Right? And so you can draw a little stack on the left, and you can sort of see what the values are being pushed and popped. And that's actually one of the things you have to do in lab 1. Right? And then it does actually the work. Pushes $8, correct? That is the value that's the argument, and so it pushes it on the stack. Calls f, and then that will turn the EIP, correct? Will point to the first instruction of f. And what in the first instruction of f actually pushes the EBP, the frame pointer, the base pointer of the callee, saves it, sets up its own frame pointer, EBP, and then it pushes its argument, which is x. And if you think about it there, okay, we can draw a little picture, right? So the stack is broken down on the x86. And so we look at this in a set of instructions. The first thing was EBP was pushed, correct? Then stack pointer was, then the EBP register points to the current stack pointer. Then we pushed 8. Then we called f. So what is the value that's going to be pushed here? Yeah, go ahead.
EIP?
Yeah, what is the EIP going to be? Yeah, go ahead.
It'll be the address of add L1
Yeah, right, the first instruction after the call instruction is going to be there. So it's going to be whatever that address is. So let's, do something stupid and say 1, 0, 1, 2, 3, 4. And we just push 4 here, right? So that's the address of the, but that's putting whatever is, that is the end long. Right? And so that's that. And then we're seeing that we're pushing on the EBP again on stack pointer, or whatever this was. We're going to push that on the stack. And so where is this value? What is this actually? It's really pointing back to this point, right? Okay. Then we move whatever was ESP into stack, so that's going to be pointing out here, right? And then we're doing 8 off the stack marker works out. So stack point is also pointing here, right, at this point. And so what does this push L, with the displacement, 8, whatever, parentheses open, dollar, or percent ESP, what does that do? What does that instruction conceptually do?
Addresses positively off the stack pointer.
Yeah.
So
What is there?
your argument.
My argument, right? So there's 8 of ESP, so happens to be also 8. But that's a coincidence, right? Because that's the value actually pushed. That was the argument that main actually pushed to F, right? So this is how F finds its first argument, right? Its only argument, namely 8. Okay, so what do we do with that? We push that back onto the stack, right? So that's going to end up here. Okay, and then we call G. Right, so let's keep going. So this is basically, I guess whatever. So this is the stack frame main, right? And this is then the next in the stack frame. And then we're going to go further. So did I push the 8 already? Sure. Yes. And so we're going to call E. We're going to call G. So what's going to end up in the stack when we do the call of G? What's call pushing on the stack? Yeah, it's going to move an instruction pointer, correct? And it's going to be the return address right after the G, which is the move long EBP ESP, correct? Which, whatever. I'm not going to write it. Some address. And it corresponds to the address for move long there. Okay? And then, that call instruction will set the EIP to point to G, right, to the address of the first instruction of G, which is going to be push EBP. So it's going to, whatever EBP is pointing it right now to, which is that one, it's going to push that on the stack, EBP. Right. And then it's going to set the move long EBP to the, okay, I got to go to G, yeah, move push EBP. Then move long stack pointer into EBP, so whatever the stack pointer is currently pointing to, that is where EBP is going to be pointing to, so EBP is going to point in here. Right? And what's the value that actually is in here? Well, that's the value, this basically points to here, right? So what I allow the EBPs to do, it's going to be very important in lab 1. When something runs wrong with some function that we call here, and we want to know how did we get there? What can we do? Sorry? Yeah, we can get stack trace, right? We can go walk back right through the EBPs, through all the stack frames, and find out who was the caller, right? And we look at this stack, and we know that the first, the top of the stack is going to be the first caller is going to be call F, and the second call G. And so it's easy for debugging, right? We can sort of find out how did we get to this particular piece of code. Okay? Where was I? I think I set the ESP. We're going to see. Okay, so we're going to use the first thing where we see caller state register. So this function G which is running x plus 3, thinks it needs EBX to actually compute the value, and so it saves the old value of the EBX first, because EBX is a call saved register. So its duty is to actually save it before using it, so it saves EBX on the stack. And then it takes move long of 8 EBP and moves to EBX. What does that do?
It's the argument to register.
Yeah, push the argument of G, correct, into the register EBX. This is why I save EBX, because we're actually going to trash it. So now EBX is going to contain what value? 8, right? So here's an interesting question, right? If you're paying very, very careful attention, which you should do if you're programming assembly, you will find out that in the first case, the argument correct of F was referenced using 8 ESP, right? There. Here in G, it actually uses EBP. Why? Why not using the same? Go ahead here.
It's because this time you actually push something onto the stack, so ESP is different than EBP, where previously they were the same.
Yeah, right. Remember in actually G, we pushed EVX on it, so the stack pointer actually pointing here. In the previous case, actually the stack pointer had exactly the same value as EVX, and the compiler knew that, and just used the ESP instead of EVX. Well, so not EVX, EBP, sorry, the base pointer, correct? So typically, actually, the way GCC typically gets at its arguments is as a fixed offset from EBP, right? Because EBP is always pointing in the right location. It's always pointing to the beginning of the stack frame. While ESP might actually be somewhere down because you allocate space for local variables. Okay? Go ahead.
Is it somehow more efficient to use ESP instead of EBP?
I don't think so.
And similarly, wouldn't it have made more sense to use ECX or EDX since we don't need to save it?
Yeah, there's a lot of things that could make a lot more sense, correct? In fact, the right way for the compiler to generate this code would be just to say, move long $11 into AIX.
If you pass dash O to GCC, it'll do that.
Yeah, so I was going to say that. So, the good compiler, if you run, exactly as Austin said, if you compile the same piece of code with dash O2, you're going to get that. And so the compiler is a wonderful thing. It should all take 6035, just to see how actually real compilers work. Because this is like this, this is sort of the literal translation if you don't do anything, smart. And in fact, you have to do a bit of work to actually get this out, because the compiler generally just want to be smart, right? Like very few people are interested in actually generating stupid bad code, except us, because we need to understand what's going on. All right, all make sense? So this should be hopefully help you tremendously with lab 1. So if you want to reference, so if you want this, so this notation, correct? This EBP8 finds the first argument of the function. So how do you get the second one? Third, fourth. Good. So you can do it, and then what is the advantage of doing it in reverse order in this way? So like any particular, why not do it the other way around? You could do it too, but
Makes the math easier.
for what?
People.
Close, but not.
Like the first argument is always the same.
First argument is always in the same location, but why is that? Nice.
Good. The arguments are pushed onto the stack in reverse order.
Yeah, why?
We know how many arguments.
Sorry?
We know how many arguments we're given if we push the number of arguments in the first value.
Yeah.
Well, it's because we're not always going to have the same number of arguments, so it's good for the first argument to always be in the same place.
Yeah, if you have a variable number of arguments, you do it in reverse order, you don't really know where the first one is going to be, all right? So unless you do something special. In this way, you don't really have to do anything special. Well, the special thing you're doing is pushing them in the reverse order, is that the first argument is always going to be 8 of EBP, the second one is always going to be 12 of EBP, right? Make sense? And you will see more of that in lab 1. In fact, I think we have a challenge or a little problem there that you have to design a calling convention, or at least think about a calling convention that allows you to do not reverse order, but still have variable number of arguments. You could imagine doing that. Okay? So here's all the action, right? What this drilling program does, it actually does the real work, adding 3 to the value as EBX, correct? And there was 8 in EBX, and so EBX is now going to have to come to 11. And then it moves EBX and AIX. Why do that? That's the return value from G, correct? So when G is returning, it has to return, it leaves the return value in EAX. That's part of the contract. So EAX is going to have the value 8. Okay. And, oh, sorry. 11. And then now we're basically going to go do the epilogue. We're going to restore values. And so why do we restore EBX? What's that going to do? Yeah, we're going to, let me make sure it actually did it right. Do EBX, and then we pop EBX, so we're going to get rid of this guy. Right, so the step point is pointing right there now. And what this pop, so this is an important instruction, correct? What's going to happen now? We're going to pop whatever is on the stack, correct? And we're going to put that value into EBEP, correct? Well, where's the stack pointer pointing to? It's actually pointing to the saved EBEP. So what we're basically effectively doing, we're restoring the EBP. Right? And this will result that EBP now, where it's going to be pointing, well, it's going to be pointing, back here, right? And so basically we restored the EBP correctly, so that now if F wants to refer to like its core argument or a third argument, that actually can generate the code, whatever, A EBP or something, right? So we're almost done. So now this one is off the stack, right? Stack point is going to point into here. And so we're going to do, we'll move EBP to pop EBX, that's good. Oh, we already did this, we did this. And we're going to do we did the pop, and then we do the return, and the return is going to it's going to pop off this value, correct, and put that in EIP. And that happens to be, correct, the correct instruction, because that's going to get us exactly to the next instruction after the call to G. Right, so now this is gone. And so basically the function, the execution of function G has completed. All right. So now we're back in F, correct? And the first thing we're going to do is move along EBP into ESP. What is this sequence of instructions going to do? These 3 instructions. Yeah, we're going to basically do the same thing, right? And we're going to now make EB forward back to here. Right? This is the epilogue of F. F doesn't do anything with AIX. And it's supposed to use AIX for its return value. Is there a bug in this code?
It's returning something that was just returned to it.
Yeah, and there's no change to whatever it was returned to it, so it can just, AIX still contains 11, so we're still in great shape, right? So it didn't violate the contract. It's just a little, tiny little bit smart, right? We're really stupid if we're like, whatever, done something redundant. And so basically now we're going to do the return. Well, the return, okay, so this stuff is gone, correct? That is gone. So now we do the return. Remember, this was an address, right? This is the address with the instruction right after the call to F, the 4th instruction, right? And that is that add long instruction. So we're going to return there, and this one is gone. All right. So now the EIP is pointing to the instruction add long, and that does the final part of our program, right? It adds 1 to the content of AIX, which was 11. So now it will be 12. All right. And then it actually does the epilogue of main. Okay. We're all maybe slightly boring to do this so mechanically and make sure, but it's very important to understand this. And so when you're, particularly, it's important in lab 1, but more importantly, it's going to be a very important in later labs where if you get this wrong, and you set them, because in a couple of places, we're going to set up our own stack frames. And those text frames really have to adhere to exactly the semantics that our version of GCC is using, right? Okay, good. Like one final, so we compiled this program basically, or at least we looked at it, like what the assembly does and why the C and the assembly match up. And generally you can do this. You can look at the sort of a C program and sort of figure out, well, this sort of roughly the assembly that should, well, the non-optimized version of the assembly that should be. Right? And that's a very worthwhile exercise to do if you look at parts of the assembly code. In fact, for all the programs in Josh, for the kernel, for the bootloader, and for any user application, the make file actually generates also the assembly file. And normally the compilation process all throws that stuff away because there's no reason to look at it. For us, it's often so important to know exactly what's happening and which instruction, like you're debugging your kernel, we'd like to know exactly which instruction you are. And some C instruction might be many, many assembly instructions. And so you can just walk through one by one and look at the .asm files and sort of find out where you are in the execution. Okay? So just to do as a final step, one we're how do we get actually to a running program? Right? We only saw the first phase, namely going from .c to assembly. Many programs, including the kernel, have many, many C files. And so it may be references from one file to another file. You may call a function, G that actually stored in some other file. And so what the compiler does, basically it compiles each, GCC compiles each file separately to assembly. The assembler, turns that into bits. And usually picks the right representation for the opcodes, for the argument encoding and all that kind of stuff. And so you can just look at it and understand like how actually the processor interprets the instructions, and that's actually real bits. And then all those, that produces what we call a .o file, an object file. And those object files are combined by the loader into a single binary. And the loader, what does it, like the linker, I should say, the linker. What does the linker do? Well, if there's a function f that was defined in another function in another file, then the linker will go and find the address of that function, put it in the right value in that particular object file so that it all actually works out correctly. Okay? And once it's linked, then the loader actually loads the program into memory. And as you will see in Josh, the loader actually, the program is linked at one particular address and loaded in a different location. And you will see that in lab 1 a little bit more. Okay? Okay, so there's a lot of the infrastructure. There's one piece remaining, which I talk a little bit about the emulator. Instead of like taking that hardware box that I just passed around, you don't run actually your JAWS kernel straight into hardware. You could totally do this, but it'd be just very painful because just rebooting actually, pressing on off and waiting for the computer to start actually takes a little bit of time. And since we're counting on the fact that you're going to be reasoning your computer a lot, it's much easier to use an emulator. And so the picture that we basically have, right, is that you're running some PC, well, some laptop, running Linux. On top of that, you're going to run this program QEMU or box that emulates a PC again. Right? And on top of that, you're actually running the JAWS kernel. And so one of the, and so there's a piece of software, right, that emulates the PC exactly as the real one. And so this sort of like makes clear that, right, that hardware software is not really any real difference. Right? So how does this work? I'm going to talk a little bit about like the piece of program, right, that actually emulates the PC, so you even better understand the PC. So the emulation of memory, the QEMU basically defines a bunch of variables. C variables that correspond to the registers. Right? We'll have an EIP, say local variable of global variable EIP, some secondary registers, and basically represents the memory as just a big array of characters. Right? And in this case, 256 of them, because we're running mostly QEMU 256 megabyte. Right? So that is, and there are 8 registers because the x86 has 8 registers. Right? So that is like your registers and memory. You have simply the processor is emulated. It's straightforward. It reads the instruction. right, which is actually on x86, as I said, slightly complicated because you have to decode the opcode, and that will tell you whether you should get 1 byte, 2 bytes, 3 bytes, 13 bytes, or 16 bytes, right? Whatever it is. So actually decoding an x86 instruction is slightly, reading it is slightly complicated. Then it's being decoded, right? And we'll look at the opcode and deciding the opcode what needs to be happening. And depending on L, B, and W, it might be a 1 byte operation, 2 byte operation, or a 4 byte operation. And you see what happens here, correct? We see an opcode add. We find the source and destination out of the instruction, and then basically we just update the registers, right? And that's what the QEMU does for you. And then in the end, we update the EIP, whatever the instruction length, correct? So it just simulates or emulates the hardware completely faithfully. It has to do it, correct? Because the software you're running on, it expects that it actually can run on the real hardware. So there should be no difference basically between the real hardware and actually the emulated hardware. So is this going to run as fast as the hardware, the real hardware? Again, you might have wondered why you built any hardware at all, right? So how much slower is this going to be? Once, in fact, twice as slow, 10 times as slow, 100 times as slow, just eyeballing, just like thinking about this.
1,000? 1,000?
Yeah, many instructions, correct? Because to execute a single F instruction, how many instructions are we executing? Lots of them, right? Because we're reading the instruction, we're decoding it, then we're updating the actual register that corresponds to the actual instruction that the hardware is supposed to be doing, and all the other stuff is just overhead, right? It's just like emulating the processor. So it's going to be many, many, many instructions. Now, you notice, where's run QEMU so far? Good. So, did it feel like it was a factor 100 or 1,000 slower? No, it isn't, right? And why is that the case? Yeah, that's one part of the answer, but not the full answer. So QEMU, well, it depends on which emulator. If you run QEMU is actually extremely smart. It actually takes a whole bunch of blocking instructions that needs to be executed or emulated, and actually generates the equivalent x86, real x86 code for it. So it doesn't really emulate them, it just executes them. And so in that way, you're going to get basically a lot of the time you're going to be running at sort of hardware performance because it's doing exactly the same thing. Okay? So instead of doing this on any individual instruction, it actually does it on basic blocks, and then it's very smart about how to combine the basic blocks, and there's a huge number of optimizations that make it run fast. To the point that basically you can just boot Linux on it, and so it feels like a normal computer. Okay? How does it emulate memory? Well, it knows exactly what the physical memory layout is, correct? And so it emulates that faithfully. It has, if it is a low memory, runs it out, turns it at low memory. It's a BIOS operation, it will turn it out to BIOS. If it's at an extended memory, it will turn it out to extended memory. So it just emulates the whole PC platform completely faithfully. Similarly for write. And of course, then it has to emulate the devices too, right? Like all that stuff that's on that hardware platform, it has to emulate too. And so there's basically a piece of software that just emulates the devices out. Typically, you can implementing the disk drive is pretty straightforward because you can use the local file system to do it. Right? You don't actually have to store the guides. You can use the file system of the underlying operating system to do it. Which then typically is called the guest OS. Okay. So that gives that a reasonable sense about how to. Hopefully you have a pretty good picture about the infrastructure that you're using. So if you have any questions about it, this is a good time to ask them. Okay, so very quickly, and then we'll switch to real code. So the most lectures are to form a little bit of sort of general material, and then looking actually at XV6 to sort of see actually how it all comes together in real operating. Real operating system is not really real, but you wouldn't want to run it for real, but it actually does everything what an operating system supporter more or less supposed to be doing. So, this is like a huge quick review of what an x86 is, and basically, it's sort of an illustration of some big ideas going out of computer architecture, computer organization to how they sort of manifest themselves in x86, right? So there's a whole idea of a stored program computer, stack, memory, I/O, and basically you saw this sort of hardware, software, these platforms such as QEMU, virtual machines, etc. Right? And if you're not a very sophisticated or experienced x86 programmer, you're likely to be slightly intimidated by the amount of information, but you will get, as you go through and start building, software and, looking at x86 instructions, you'll pick it up very, very quickly. There's not that much specifics. There's very much, so the data is slightly different, but the same concepts. Okay, so what I want to do next is look a little bit at the bootloader. Right? So when the operating system, when you press on off, correct, on the computer, something has to happen. And so before the first instruction actually gets to run, then you more sort of understand a little bit of like what actually does happen. And so it turns out that story is complicated, and we're not going to completely get to the depth of it. But at a very high level, when you press on off, there's going to be a piece of software that runs that's going to load the kernel into memory so that at some point the kernel of the operating system can run. And that's done by the bootloader. So we're going to talk a little bit about the bootloader, and then once we understand the bootloader, then the bootloader will load either JOS or XV6, and then we start executing the operating system. In your case, JOS, in our case, XV6. And the bootloader between JOS and XV6 are very similar, almost identical. Because we don't want you to spend a huge amount of time, thinking about bootloaders, but we also don't want to hide it from you, so that you're sort of, a lot of 828 is like removing abstractions, really understanding actually what's happening. And so we look a little bit at bootloaders, and you have a reasonable sense. Okay? And so lab one, most of what you're looking at is actually bootloader code to understand actually how your operating system actually, gets off the ground after you press on off, correct, on your PC. Okay? So let's look at that.